All right, so the thing that students initially trip up the most on in organic chemistry is nomenclature, right? So a big part of any professional career is learning the language, and organic chemistry, but organic chemistry in particular, has a very large vocabulary, and it's important that you learn it. And in some ways, you kind of have to treat it like a foreign language, but it's like a language, highly structured, and it has rules that, like a language, for the most part, it follows, for the most part. And the first step in learning these rules or learning these names is to start out someplace where we can all kind of agree sort of the nexus of organic chemistry, and that is with the hydrocarbons. So hydrocarbons are molecules that just contain a hydrogen and carbon. And so that's it. So pretty much anytime we draw one of these little structures here, it's a hydrocarbon, right? Even though I've not drawn the hydrogens, you still know that there's 1, 2, 3, 4, 5, 6 carbons here, and I've called that hexane before, but you probably don't know where some of these names come from or how they're generated, all right? And so the most basic hydrocarbons are what are referred to as saturated hydrocarbons, okay? And you've probably heard the term saturated fats, and in a saturated hydrocarbon, that just pretty much means all carbons are sp3 hybridized, okay? So, in other words, there's no double or triple bonds. And so a saturated hydrocarbon is called an alkane. All right, and that is a saturated hydrocarbon. And an alkane, now if you have a double bond, all right, so if it's not saturated and say you have a double bond, right, so you have a degree of unsaturation, or you can say you have a double bond, those are called, again, hydrocarbons, as in they only have CNH. Those are called alkenes. An alkene, that has a double bond. And it's got a double bond in it. So an alkane, saturated alkane, we already drew this 1, 2, 3, 4, 6. 2, 4, 5, 1, 2, 3, 4, 5, 6. 6. An alkene would have a double bond in it. So then we just draw the same molecule, but now we put a double bond in it. All right? So that is an alkene, which means there's a degree of unsaturation. And so an alkene, really, that just implies an sp2 carbon. Alkane, all sp3. Now you notice I didn't say all sp2. An alkene just sort of refers to that bit, right? You can call the whole molecule an alkene because it's overriding functional group. The thing that's probably going to do the chemistry is this double bond. But the alkene is sort of that double bond right there. And this will become a little bit more clear as we start using the language. And just like any language, it doesn't really make sense until you start using it. Now, what about an sp hybridized carbon, the old triple bond? Those things are called an alkyne. And an alkyne will have a triple bond. That's 1, 2, 3, 4, 5, 6. I've added an extra. Let's get rid of that. There. We put an H on the end. 6 bonds there, that's an alkyne, or a triple bond. And sp hybridized, alkyne. All right, so these are your predominant hydrocarbon families: alkanes, alkenes, alkynes. And alkanes, there are all kinds of alkanes. So let's start off with alkanes, all right? So you remember, of course, that a carbon has an octet, right? And a hydrogen is usually an implied atom here. And that we can draw this around like that. And we've kind of taken in to be a little bit lazy, especially if we wanted to say, so this is methane, just CH4. But if we wanted to, say, draw ethane and alkane, right, we could, again, just draw a connection here and then fill it in with the substitutions, as it turns out, as hydrogens, right? Now, and from here you can build, and typically the way I've drawn it is like chains, right? So if I draw that, we don't draw the hydrogens, you can reasonably assume. That's 1, 2, 3, 4, 5. It's 5 pentapentane, so then when that becomes pentane. Of course, these don't have to be hydrogens, and we've seen examples where that's not. An alkane, of course, can have substitutions, so you can draw a pentane, 5 carbons, and you can draw it like this. So 2, 3, 4, and then that's a 5. So that's again 1, 2, 3, 4, 5. This molecule is not called pentane, but it's got 5 carbons just the same. You can draw, it's not pentane. Nope. But a 5 carbon ring. But you can continue to add different substitutions. You can have something called neopentane that looks like that. 1, 2, 3, 4, 5. Pentane? Nope. Not called pentane. But they're hydrocarbons nonetheless. So how, if they're the same, structure, so if we remember how many hydrogens that are on this side, there are 3 hydrogens there, 2, 2, 2, 3. So that would have 12 hydrogens. Over here you have 3, 3, 2, how many there? Hopefully I said 1. 3. So that has 12. And then here you have 3, 6, 9, 12. And so all of these have a formula of C5H12. So how do you even go about naming this craziness, right? And that's what we're going to talk about here. Obviously, you can't refer to all these as pentane. You have to come up with a name and an associated structure with how you're going to name all these substitutions. So first, we kind of have to discuss why that's a pentane. I think you can probably figure the Greek bits that 5 carbons are pentane. In fact, we can go ahead and write this down, that if we just write the number of carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? The number of carbons, basically starting with 5, it's all Greek. That's pentane, and then 6 would be hexane, and then 7 would be heptane, 8 would be octane, 9 would be nonane, and 10 would be decane. And then, you could keep going if you know French, right? Because 11 would be un decane, and then 12 would be deux decane, and so on. Maybe it's not French. I don't think 13 is trois decane, but it follows the Greek. First 4, on the other hand, don't. First 4 are sort of legacies, if you will, and they come from different things. One carbon is called methane, and methane does not come from meth as in the smoky little crystals that get you high. It comes from the Greek word that means wood. Because in the early days, and even today, if you go out and you find some wood and you try to distill it, you'll get methanol or wood alcohol. Look at ethanol. So you get a lot of methanol. And of course, if you drink methanol, you go blind for various reasons. Not a good idea to drink it, but that's where it comes from. The Greek word for wine or spirits. Now, ethyl, oddly enough, the eth root word actually comes from colorless. So ethyl alcohol is, of course, colorless. Ethanol and ethyl ethers are all colorless liquids. So it's kind of funny that meth came from the spirits, when if you drink methanol, you go blind, whereas eth came from colorless, which I guess is true enough, but I don't know. Why didn't anybody ask me? I wasn't alive. I would have done it differently. 3 is prop. So methane, ethane, propane, and propane accessories that was prop. That is named after first fat. And that might take a little bit of explaining. Propane comes, so, all right, you want to know, I know you want to know. So you know acetic acid, right? So acetic acid has 2 carbons, 1, 2. There's also another acid called formic acid, and it looks like that. All right. Now, formic acid, I guess, is made by ants or something, and so it comes from ants. Acetic acid is a distillation or a byproduct of fermentation of alcohol to make acetic acid, which is in vinegar. Propionic acid has 3 carbons, 1, 2, 3. And it turns out that formic acid, that's soluble in water. Acetic acid, that's soluble in water. And then propionic acid, that is not soluble in water. So it is the first and the lightest. It is the first in this sequence, which I actually drew out of order, but you're smart students. 1, 2 carbons, 3 carbons. The first in the sequence to be a fatty acid, hence first fat. And that actually also explains where 4 comes from, the but and butyric acid. And butyric acid, as it maybe comes from, it would be convenient, and I'm pretty sure it's true. So 1, 2, 3, 4 OH. That comes from this compound, another fatty acid called butyric acid, and that is essentially rancid butter, or at least it smells like rancid butter. So I would assume it's in butter that has rancidified. So these odd, weird things, butane for 4 carbon, propane for 3 carbon, ethane for 2 carbon, and methane from 1 carbon, all have sort of weird appendages, right? So, all have weird origins, but they work. Methane, ethane, propane, butane. And then you get to pentane, hexane, hexane, heptane, octane, nonane, and decane, right? And we add these words ane to the end because that's how we know it is a hydrocarbon. If I told you methane, ethane, propane, you would always draw the same structure. You would always draw methane, you would draw ethane, propane, butane, pentane. 1, 2, 3, 4, 5. And now that we've got some kind of language going on, we can start to see how we can assemble molecules, right? So if you want to imagine drawing something like a pentane with a thing coming off of it, so that's 1, 2, 3, 4, pentane, 5 with a thing coming off of it, you can, right? Because now you've got a pentane with a substituent on it. It's called a substituent, and depending on what the substituent is, if it's a methane that's sticking off of this pentane, we obviously wouldn't call it that. We'd call it a methyl substituent. And if we have a substituent coming off of here, that's a CH2. We'd call that an ethyl substituent. Sometimes these hydrocarbons come in a ring, so you know it's not uncommon to encounter something that looks like that. All right, a cyclopentane. So when you want to start naming something like a cyclopentane, you start to see that there's like this root word associated, and that root word is pentane because that's 3, 4, 5, and that's a pentane. And then you can start adding modifiers to the front of it. So I said that was a cyclopentane because it's a cyclic system, and so we would just start off by calling that cyclo. So we'd have cyclopentane, right? And if I wanted to stick a substituent onto it, I can. If I wanted to stick a methyl group off of it, I could call that right here. And what would that be called? Let's just move this over. While you're thinking about that very hard problem, hopefully you came to the same conclusion that that would then be called a methyl cyclopentane. So these words, these structures, they start to build on each other. You've got your root word, and then you've got sort of the descriptors that start to fall out. So this is easy enough when there's only one substituent or it's a small molecule. But we're going to need some pretty substantial rules as these molecules get larger. And those rules come from the International Union of People and Cows Nomenclature. So it's not actually the International Union of People and Cows. Of course, is the International Union of Pure and Applied Chemistry. So IUPAC, as it's called, sort of has a couple of rules. And the first rule in IUPAC is, obviously, tell all your friends about IUPAC, which is also the second rule. But the first real rule of IUPAC is to find the longest chain. All right, and this is your root name. So what do I mean by that? So if I have a molecule that looks like this, I have tricked you, right? Because you're going to be like 1, 2, 3, 4, 5, 6, 7, 8. Ah, that's an octane. But that's false. You have to find the longest chain. If you can't counting from 7, that's 8, that's 9. So actually that's a nonane with a methyl group on it. So always be on the lookout for these sorts of tricks. They're there to trick you, right? So find the longest chain, no matter how it is configured. That is a 1, 2, 3, 4. It can be no matter. So find the longest chain, no matter how it is configured. So there is plenty of reason why 1, 2, 3, 4. You don't go that way. 5, 6, 7, 8, 9, 10. Ah, see, you can become quite tricky. All right, so the longest chain, and that would be a decane, by the way, with an ethyl group, or the ethyl group and a methyl group here, coming off the other side. And so any carbon that's not on this chain, so any carbon not on the main chain is an appendage. All right. Doesn't really make, but it's going to have a name. We're going to have to account for it. So when you start counting, count it unlike what I did up here. All right, so I started randomly because I was just looking for the right chain. But the actual rule is number the chain starting to the closest first appendage. You'll notice in both cases up here, I totally did the opposite. But if I have something that looks like this, and I know that this is going to be my longest, I actually start counting down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So I actually have to start numbering here. And this is the important numbering because this is the numbering that we're going to use to name it. Of course, you can count in any direction you want to find the longest chain. So you can count whatever direction you want. Find that's no name. But IUPAC law, and you will go to prison if you break it. IUPAC law says that you have to start numbering down by the nearest appendage. So whatever thing that comes off that chain, right? And then these appendages do have some names. So name appendage according to carbon count. Right? So if my appendage coming off here is a CH3, then that's obviously a methyl. And then we add the "ill" to the end because that makes it like an adjective, I guess. I don't know. It clearly indicates that it's an appendage. If I've got 2 carbons coming off here, that's an ethyl. Ethly. All right. And then you can have propyl, butyl, pentyl, hexyl, so on and so forth. And if you have multiple appendages with a bunch of things, put appendage names in alphabetical order. Whoop. Put appendage names in alphabetical order. So A, B, C, D, E, ethyl would come at first, then methyl. So if we had ourselves something that looked like this, 2, 3, 4, 5, 6, 7, 8, 9. Right? So then this would be, we would count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, this is a decyl chain. An R. So this is decane, right? And except we've got a 2 ethyl and a 5 methyl. And then we can just take this little feller, doop, 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 add it right there, boom, there's your name. 2 ethyl, 5 methyl, decane. Okay. One thing to add though, if you have a modifier like say di, tri, if you have like an italicized, you see an italicized N, or you see a T, which usually means there's something called a terbutyl. Those are ignored for the alphabetizing. Okay, you kind of want to ignore these. And then when you have some things like halogens, should have an O suffix. All right, so if you want to say, I want to make 2-bromobutane, that would be understood to be butane. Doot, doot, doot. 1, 2, 3, 4. And I've already conveniently given myself the number 2 right there. So I'll just put 2-bromo, right? So we can do a number of these, and they can be pretty straightforward. And we have our modifier, so let's give it a shot. So let's go down and just say octane. And in the context of, if it's going to be cyclo, right, if you're going to make it a cyclic system, that's always got to go right next to the octane. So cyclooctane or anything, the cyclo always comes right next to it. So the cyclo has to go right there. So we're just going to put a cyclo here and put it right next to, take that cyclo and put it right there. So that basically guarantees us that we've got to draw a cyclic octane molecule, right? So we're going to draw a stop sign. All right, easy peasy. Now, we're going to start off with, let's see here, what do we want to put on here? Let's say we're going to put on a bromo. Then we're going to put on an ethyl. Let's say an ethyl. Ethyl's fine. Ethyl. And then where are we going to put them, right? So let's just make our decision here. Let's put a bromo here. And we'll put the ethyl here. So you always start counting based on the alphabet, so bromo would come first. And because it's a cyclic system, we're going to start at bromo as being number 1. 1, 2, 3, 4, 5, 6, 7, 8. All right. And so in this particular case, that's going to be a 1 bromo and a 4 ethyl. All right, and then we can start assembling. So ethyl is not first alphabetically, so we have to rotate that around there like that. Yep. And then I'm going to take this right here, and then go back to here, 4 ethyl, and then 1 bromo, boom, 1 bromo, 4 ethyl, cyclooctane. Works pretty well, eh? Right? Then you can have some kind of crazy stuff, right? So what if that were something that looked like that? You know, now what do you do? So some of these weird bridged carbons, they start to have they appear pretty frequently. So you can have some pretty frequently appearing and also IUPAC kosher nomenclature, depending on substitution patterns. Let's say I wanted to come up with a name for something that looks like this. You'd start writing your root name, right? You'd have, okay, cyclohexane. This is 1, 2, 3, 4. So what are you going to call this bizarre thing coming off the cyclohexane chain? Well, it's going to be in the 1 position of the ring, so that's a given. But what you actually end up calling this is something bizarre, like 1,1-dimethylethane. Ignore those red marks. 1,1-dimethylethane cyclohexane, which is kind of a mouthful, right? So these substituents that I've circled here happen pretty frequently. These small, highly branched hydrocarbons. They happen frequently enough where there are some common names for them. And the common names of substituents All right, so for now, and this will be true for a lot of compounds, but let's just say substituents off of a cyclic system. So we're going to stay with cyclohexane. We're going to imagine what happens when to sort of differentiate a cyclic system, like say this one, cyclohexane with something that looks like that versus a cyclohexane that looks like this. Okay? So both of these are cyclohexane with a butyl substituent. So you got 1, 2, 3, you got 1, 2, 3. So basically a propyl substituent. Here you could say 1-methyl ethane, and this is propyl, or you could sort of appreciate that these are both propyl substituents, so you don't have to get knee-deep in the weeds of IUPAC. So you could say instead that this one up here has an N-propyl chain, so it's a linear chain, as in N for normal. And then this has a propyl chain up here, but it's got something special. It's called an isopropyl. And an isopropyl group, you know about isopropyl alcohol. An isopropyl group has this sort of forked look to it, right? So if you talk about isopropyl alcohol, then of course you're talking about something that looks like that. So that's your isopropyl group right there. But it's just convenient then, rather than saying 1-methyl-ethyl all the time, you just use the word isopropyl. And then, of course, we like the iso. And then we like the iso because it is an isomer. An isomer of propyl. So that's, now you can get larger, so there are only a couple of things you can do with propyl, but when you get to 4 carbons, all right, so we'll stick with our cyclohexane, and then I'm going to switch to these substituent groups because there can be a couple of them. So at least 4, so if we just simply talk about 4-membered rings, I can think of at least 4 substituents. So I'm going to draw 4 cyclohexanes, because these are all going to be different cyclohexanes. One's going to be N-butyl cyclohexane, isobutyl cyclohexane, sec-butyl isohexane, and tert-butyl cyclohexane. Very much simpler to write than their alternative. So if I was going to tell you I want N-butyl cyclohexane, right, and I'm going to say, draw me N-butyl cyclohexane, you could probably guess from above that N-butyl cyclohexane is going to have a normal straight chain butyl chain thing coming off of it. So that's 1, 2, 3, 4, right? That's your N-butyl chain. Now, if I were going to say, now I want an isopropyl cyclohexane, isopropyl has 3 carbons, we're talking about 4. Isobutyl chain, you know what isopropyl looks like. It's got like this forky looking thing. So isobutyl just has gonna have, you know what isopropyl looks like. It's gonna have to have another one of those sticks coming. So we got 1, 2, 3, and 4, right? Whereas isopropyl, of course, just has 3 carbons. This has 4, and so this has an extra CH2 on that side. Now, what about if you were to take that extra carbon and it were going to come off like that, right? So now I've got this as a CH, a methyl sticking out here, and that's a CH3. That actually has a name too. That's called sec-butyl. All right, so I could say, draw me a sec-butyl cyclohexane. Draw me a sec-butyl cyclohexane, and you would draw that. All right, and then there's this fully saturated monster called a tert-butyl. Kind of drew up there, and that is your tert-butyl. And of course, they don't need to be cyclohexane. I could say, tert-butyl alcohol, and so instead of a tert-butyl cyclohexane, I say, draw me a tert-butyl alcohol, and you know what an alcohol is, that's an OH, and you know what a tert-butyl is, that's got to have 4 carbons, 1, 2, 3, then it's your 4th carbon, and then off there is going to have to be your alcohol. So if I were to say tert-butyl alcohol, you would draw me that. If I were going to say like tert-butyl cyclohexane, you draw me that. So it should start to make sense, right? You're just sort of sticking names together, sort of like conjugating a verb, right? And you can see the difference here between these different substituents, right? So in this particular one right here, all the way over here, these are totally normal. They've all got two hydrogens coming off of them, and 3 hydrogens over here. So that's just your normal straight chain butyl. But this one, this carbon only has 1 hydrogen coming off of it. And just like that one only has 1 hydrogen coming off of it. And then this one has no hydrogens coming off of it. And as it turns out, there's actually nomenclature for that as well. If you have a carbon with no hydrogens coming out of it at all, in the case of a tert-butyl, we like to call that a tertiary, or like a 3rd degree, tertiary carbon. So a tertiary carbon has no hydrogens coming out of it. Now, if you've got in your sec-butyl and your isobutyl case, these both have 1 hydrogen, and we both like to call these secondary carbons. So they're secondary carbons. And then in a normal chain where you've got like 2 hydrogens, we like to call those primary carbons, all right? You can get some pretty complicated stuff in the process of translating a picture of a molecule, or what we call a structural formula, into a IUPAC name. So there's a logical sequence that goes into this, and I'm going to help you with a fairly complicated looking molecule. Now, in a structure like this that I've drawn here, you notice that there is a 1, 2, 3, 4, 5, 6, 7, 8 membered ring, and off of there that's a 1, 2, 3, 4 carbon substituent, and off of this one there's a 1, 2 carbon substituent. So there's a lot of stuff going on. Now the ring has 8 carbons, none of the substituents even come anywhere near that, so the ring is going to be the root word because it's the biggest one. Rarely do you find a ring on a super long chain. So usually the ring is the root word, and in this particular case it is. If this were a 10 carbon chain, the ring would be called the substituent, and that naming would be a little bit hairy. But from this one, and from our last talk, we knew that the first thing we described in this particular thing is a root word, which is octane, because it's an octane group, and that group is cyclized, so it's a cyclooctane. Okay, and so the substituents, and there are 2 substituents that come off of it, are these 2 right here. And so the easiest way to name them is to just call them by their IUPAC name. You can look at this and say, well, that's a secondary carbon right there, and that looks like some sort of isobutyl or isopropyl, but it's not, right? It's not. That's 1, 2, 3, 4. That would be isopentyl. Now, if you want, just name things their very simple IUPAC name. And the very simple IUPAC name is to substitute, just make this quite simple here. That's just a butyl. All right? Just call it a butyl. All right? And the butyl has 3 substituents coming off of it. 1, 2, 3. And it turns out all 3 of them are methyl, so that kind of makes things pretty easy to put together. And you've got a trimethyl group, and to indicate where they are on this chain, and so we started numbering closest to the ring, closest to the initial part, that would give us a 1, because there's a methyl on the 1 carbon, there's actually another methyl on the 1 carbon, so that's 1, 1, and then there's a methyl on the 3 carbon, so it's 1, 1, 3. All right, and it's a 1,1,3, and I've kind of put this over here a little bit too far, but it's a 1,1,3 trimethyl substituent. In fact, it's a 1,1,3 trimethyl butyl substituent. And then that substituent over there is 2 carbons, so that's going to be an ethyl. And now we have our substituents labeled. And we've got an ethyl. That's early on in the alphabet is an E. That beats methyl. Remember, we ignored the tri, so the methyl is going to come first. Or the ethyl, I'm sorry, is going to come first. And so that's easy enough. It starts on, if it comes first, then it must be carbon 1, so that's going to be 1-ethyl cyclooctane. But we also have to account for this big thing right here, and that's the 1,1,3 trimethyl butyl, and that comes third. So how does that look? Well, we take this little bit here, and this little bit here. We don't need the little thing there. And we can put that into parentheses, and we're going to label that as a 3. Okay? So now we got 1-ethyl, 3, 1,1,3 trimethyl butyl, cyclooctane. And we can put these now all together. To produce the name of our molecule. 1-ethyl, 3, 1,1,3 trimethyl butyl cyclooctane. Well, that's a complicated molecule, but I think you get it. The 1-ethyl comes from an ethyl group at the 1 position. I've highlighted that in yellow. The 3 comes from the 3 position in the cyclooctane. Didn't highlight that yellow, but you can clearly see the number 3 written in there in that octagon. 3, and then in parentheses, the name of the substituent, 1,1,3 trimethyl butyl, and then close parentheses, and then the root, cyclooctane. All right. That is alkanes. We will cover other functional groups. We did talk about halides, like fluorochlorobromo. As we introduce new functional groups, we'll introduce new nomenclature, and it'll all start building together.